is a long one, so I hope you'll stay with me. So first off, we need to know what a rational function is. A rational function is the ratio, thus rational, is the ratio of two polynomial functions. For example, x cubed minus 3x plus 1 over x minus 2, both of those are polynomials. X squared minus 1 over x cubed plus 1, same. You might also find that some of the terms are factored already for you, so like 1 over x times x minus 2. Okay, so given that we start with a rational function, how do we integrate it? The first step is always polynomial long division. To apply our integration tools, we want to express rational functions as p of x over q of x, that's our original rational function. We want that to be in the form s of x plus r of x over q of x, where s of x is a polynomial, and r of x is a polynomial as well, and has degree strictly less than the degree of q of x. And this can be accomplished through polynomial long division, which you can review in the first lecture video. Okay, the second step is factoring the denominator. After the numerator has degree less than the degree of the denominator, we factor the denominator. For this course, you should be able to factor quadratic expressions. For example, x squared minus 4x minus 12. How do we factor this? Well, we list some factors of 12, some ways to factorize 12 as a product of two integers. We get plus or minus 1 and 12, 2 and 6, 3 and 4, and we observe that 2 and 6 have a difference equal to 4. So the expression becomes x squared minus 4x minus 12 equals okay, we just have to decide which gets the plus and which gets the minus. Because it's minus 4, so we need the 6 to be the minus part. This becomes x minus 6 times x plus 2. Okay, that's an example of factoring a quadratic expression that you should be familiar with. Even if you don't start with a quadratic expression, you should be able to factor out powers of x. For instance, in this polynomial, x cubed minus 8x squared plus 10x, we'll observe that this equals x times x squared minus 8x plus 10. Okay. And as for number 3, we also should be able to factor sums and differences of cubes. So for instance, if I have x cubed minus 8, I need to know to be able to factor that as x minus 2 times x squared plus 2x plus 4. Okay? So that's factoring. And something that helps us as we're factoring these polynomials is knowledge of the fact that every real polynomial factors as linear terms and irreducible quadratics. Okay, so if we have a complex polynomial, q of x, you can always factor that as some constant times x minus alpha 1, some complex number, times x minus alpha 2, all the way up to x minus alpha n. And here n is the degree of the polynomial, and alpha n is a complex number. But if we want to keep everything real, which in this course we do, we're going to factor it. These roots determine how the factorization looks. If our polynomial has real coefficients, then alpha j might be real, which means we pick up a linear term x minus alpha j in the real polynomial as well, in the real factorization. Or we'll have alpha j equals some complex number a plus bi, but then we'll have another root of this polynomial, alpha k, which will be its complex conjugate, a minus bi for some k. And when you combine those, you get x squared minus 2ax plus a squared plus b squared, which is an irreducible quadratic. Okay, so that explains how your polynomial will always factor into linear terms and irreducible quadratic terms. But let's say we have a quadratic polynomial, a polynomial of the form ax squared plus bx plus c. How do we know if it can be factored? How do we know if we can say this is actually an irreducible quadratic? Well, we'll refer to the quadratic formula, which we are familiar with certainly from high school. If ax squared plus bx plus c equals 0, then the two solutions, possibly one, are x equals negative b plus or minus the square root of b squared minus 4ac over 2a. If what's called the discriminant, the polynomial b squared minus 4ac, is negative, then the quadratic cannot be factored. For instance, in this polynomial x squared plus 2x plus 5, I know that b is the coefficient of the second term, so that's 2. A is 1, and c is 5. So b squared minus 4ac is equal to 4 minus 4 times 5, which is negative 16. Because this discriminant is negative, I know that this quadratic is irreducible. And a geometric interpretation for what this all means in terms of the discriminant is that a quadratic polynomial is irreducible when the corresponding parabola lies entirely above the x-axis. Okay, so here are three parabolas that are closely related. The first polynomial has b squared minus 4ac positive, so it properly crosses the x-axis. And it would factor as two linear terms where the constants in the linear terms would be the numbers indicated by the blue points. In the second example, we have x squared minus 2x plus 1, which we know as x minus 1 squared. When you have a perfect square, the discriminant is precisely 0, and we'll have one root for the quadratic equation. Meanwhile, if you have b squared minus 4ac negative, this parabola is going to sit entirely above the x-axis, so there will be no real solutions to this equation. Okay, so now we have our, we've done our polynomial long division, we have our denominator factored. Now we need to set up the partial fraction decomposition. And the big idea in this step is to transform a ratio of two polynomials, r of x over q of x, into a sum of a much simpler form. We start with a ratio of complicated polynomials and turn it into a sum of simpler ratios, where the denominator is a power of linear terms or a power of irreducible quadratics. Okay, so let's take it a step at a time. Simplest type is when q of x factors as the product. This symbol just means product. The product of x minus ai, where all of the ai's are distinct. Okay? In this case, the format for partial fractions is simply r of x over q of x equals c1 divided by x minus a1, where this is one of the linear, this term is a linear factor of q. And this is a constant that we'll solve for later. Constant, leave unknown until later. Okay, and clearly the same is true for this and for this. Okay, let's see an example of this. So the first example is x minus 1 over x cubed minus 3x squared plus 2x. So the degree of the numerator is less than the degree of the denominator, so long division is not necessary here. Okay, as for the denominator, we want to factor that. We notice that there's a factor of x that we can pull out from the front. So x cubed minus 3x squared plus 2x, that's equal to x times x squared minus 3x plus 2. And then to factor this quadratic term, we'll notice that the only way to get 2 is to multiply plus or minus 1 by plus or minus 2. And we notice that minus 1 and minus 2 add up to minus 3. So our factorization becomes x times x minus 1 times x minus 2. Okay? So given that this is how the polynomial factors, we set up our equation, our partial fraction decomposition, as follows. X minus 1 divided by x cubed minus 3x squared plus 2x equals a, okay, this is just a constant, divided by x plus b divided by x minus 1 plus c divided by x minus 2. Okay? And that's the partial fractions decomposition. In the next example, this has already been the factorization has already been worked out for us. So all we have to do is use the appropriate format, and this is given by a constant divided by x minus 1 plus a constant divided by x minus 2 plus a constant divided by x minus the square root of 2. Okay? It's okay to have terms in here that are not rational as long as they're real numbers. Okay, so that was distinct linear terms. Now we look at repeated linear terms. The more complicated case is when q of x factors as linear terms not all distinct. We can write this in terms of powers, ri greater than or equal to 1, and we'll write this as q of x equals the product. Again, I'll just remind you that this is product of x minus ai to the ri, where all of the ai's are distinct, meaning we if they're not distinct, we group them all together, so now we have powers to the ri, which could be greater than 1. In this case, the format for partial fractions is as follows, and this looks confusing, but I'll explain it in words shortly. So if p of x over q of x equals c11 over x minus a1 to the 1 plus c12 over x minus a1 to the second power plus all the way up to c1r1 divided by x minus a1 to the r1 power. Okay, and then you do that for each root, x minus a2, x minus a3, all the way down to x minus an, where again you have a constant divided by x minus an to the first power, plus a constant divided by x minus an to the second power, etc., all the way up to x minus an to the rnth power. In words, if a factor ai is repeated, include a term with constant numerator for every power of x minus ai between 1 and ri, which is the power to which it appears in the factorization. Okay, so that might be a little abstract right now, but let's see it in an example to clarify. So here we have excuse me, x minus 1 divided by x squared plus 4x plus 4. Let's factor, again, long division is unnecessary. Oops, long division unnecessary. Let's factor the denominator. We get x squared plus 4x plus 4. This is equal to x plus 2 squared. Okay? Given that we have x plus 2 squared, we can set up the new equation. X minus 1 divided by x squared plus 4x plus 4 equals partial fraction decomposition. So we get a constant term, a constant numerator divided by every power of x plus 2 from 1 until 2. Okay, so we get a divided by x plus 2 plus b divided by x plus 2 squared. Okay? Make sure this is, oops. So we have one constant numerator here, and we get a term for every power between 1 and the appearing power. The appearing power here is 2. Okay? Let's do this slightly more complicated example. 1 over x minus 1, x minus 2 squared, x minus 3 cubed. Okay, so here the factoring is done for us. Okay, so the long division is unnecessary. Factoring is done. So now we just have to follow the rules to get the appropriate format. So here we're going to say this is equal to, well, we only have x minus 1 to the first power. So we'll get a divided by x minus 1. Then for x minus 2 squared, that appears to the second power, so we need two terms, b over x minus 2 plus c over x minus 2 squared. Now we have x minus 3 cubed, so we're going to need a term for every power from 1 until 3, which is the power that appears here. So we get plus d divided by x minus 3 plus e divided by x minus 3 squared plus f divided by x minus 3 cubed. Okay? Okay. Type 3, now we bring the quadratics into the picture. There are the cases where the denominator factors into distinct irreducible quadratics. So if we have q of x equals product of x squared plus aix plus bi, okay, and these are just specific constants, such that this is an irreducible quadratic, where all of the pairs ai and bi are distinct. In this case, the format for partial fractions is r of x over q of x equals c1x plus d1. So this is new. We get a linear term. Okay, it's not just a constant. We have a linear term here, as well as a constant term, divided by x squared plus a1x plus b1, plus up to cnx plus dn over x squared plus anx plus bn. So you get a single fraction for each factor of this polynomial. Okay, so let's see how this works. Here we have x squared minus 1 divided by x squared plus 4 over times 4x squared plus 1. So we can check for ourselves that both of these are irreducible quadratics. B squared minus 4ac in both cases is negative 4. So both of these are irreducible. And that means that this is already factored. Okay, and this degree is low enough because it's degree 2, which is less than degree 4, which we have on the bottom. Long division is unnecessary. Okay, so let's see how we would set this up as a partial fraction decomposition. We have x squared minus 1 divided by x squared plus 4 times 4x squared plus 1. And this is equal to ax plus b. Okay, again, we have that new linear term divided by x squared plus 4 plus cx plus d divided by 4x squared plus 1. Okay? Now we have something we have to factor. We have 1 over x to the 4th minus 16. So you'll note that this is a difference of squares. Okay, it's the square of x squared minus the square of 4. So we get, let's factor, x to the 4th minus 16 equals x squared minus 4 times x squared plus 4. And factoring further, we have x plus 2 times x minus 2 times x squared plus 4. And this is an irreducible quadratic, as we confirmed in the last example. So when we have a combination of the linear terms and the irreducible quadratics, we just deal with them as we would if they were on their own. So this is a divided by x plus 2. You get a constant over this linear term, plus a constant over the other linear term, plus the linear term cx plus d divided by x squared plus 4. Okay, and that's for the distinct irreducible quadratics. And finally, we have repeated irreducible quadratics. Q of x can factor as irreducible quadratics, not all distinct. Here again, we'll write it as powers of distinct quadratics. Okay, and here are the AIs, and these are really the pairs AI and BI, I should say. The pairs AI, BI are distinct. In this case, the format for partial fractions is much like with the repeated linear terms. You get a term for each power between 1 and the power to which it appears in the factorization. Okay, and each term also gets a linear term in the numerator. In words, if a factor x squared plus aix plus bi is repeated, include a term with linear numerator. Again, that's a constant times x plus another constant for every power of x squared plus aix plus bi between 1 and ri, which is the power to which it appears in the factorization. Let's do an example of that here. So we have x squared minus 1 divided by x squared plus 2x plus 5 cubed. Okay, so first thing to notice is that long division is unnecessary because our numerator has degree less than denominator. And we'll notice that x squared plus 2x plus 5 is irreducible because b squared minus 4ac is given by 4 minus 20, which is minus 16. So given that, that this quadratic is irreducible, we're going to use the form for repeated irreducible factors. So we take x squared minus 1 divided by x squared plus 2x plus 5 cubed. Now I'm going to include a term for every power between 1 and the appearing power, which is 3. So we get ax plus b, so our arbitrary linear term, divided by x squared plus 2x plus 5, plus another linear term, cx plus d, divided by x squared plus 2x plus 5 squared. And finally, the last term, ex plus f, divided by the third power, x squared plus 2x plus 5 to the third. Okay? And that is the partial fractions decomposition for this rational function. Some common mistakes that I often see when people are attempting partial fractions problems is that they'll write something like in number 1 here. So this person took x plus 1 divided by x minus 1 cubed, and they set that equal to a over x minus 1 plus bx plus c divided by x minus 1 squared plus dx squared plus ex plus f divided by x minus 1 cubed. And this is a mistake. So you shouldn't get anything like this linear term, or either this linear or quadratic term. Whenever you have the linear term in the denominator, you should just have a constant, okay, like we have here. And even when the linear term is raised to a higher power, the numerator should still be constant. And the analogous situation is true for quadratic terms. The numerator should always be a linear term, even if the quadratic is raised to a power. Okay, another problem that I see is, as in part 2, that someone will remember to have the constant over the linear and a linear over the quadratic, but they'll forget that there should be a constant term here. Okay, every linear term in the numerator needs a constant term. Great, so now we know the correct format for partial fractions of all of these different types of rational functions. Now we get to solving for the coefficients. Okay, all of these formats that we've done have these arbitrary constants in there, and now we need to solve for them. For example, in the decomposition that we did earlier, 1 over x to the fourth minus 16 equals a over x plus 2 plus b over x minus 2 plus cx plus d over x squared plus 4. We need to solve for a, b, c, and d before we integrate. Okay, so the first step towards doing that is clearing the denominators. Multiply both sides of the equation by x to the fourth minus 16. You'll notice that because x to the fourth minus 16 is equal to the product of the other three denominators here, so when I multiply by it, I get 1 on the left-hand side, and on the right-hand side, I get these two terms, and the third factor of x to the fourth minus 16 cancels, and similar happens in each of the other terms. For each of the other fractions, we're left with two of the factors of x to the fourth minus 16. Okay, so where do we go from there? So the most straightforward approach is to group terms by powers of x and then solve as a system of equations. So on the left-hand side of the equation, we just have 1. So we could also write that as 0x cubed plus 0x squared plus 0x plus 1. And on the right-hand side, we want to take all of our x cubed terms, all of our x squared terms, etc., group them all together. So first, let's figure out the x cubed terms. Well, we're going to get 1x cubed from the first term, so that'll be a. And another x cubed from the second term, so that's b. And then another x cubed from the third term, that'll give us c. So it's a plus b plus c times x cubed. Okay, now we look for the x squared terms. Well, in the first term, I'm going to have minus 2a times x squared. In the second term, we're going to get b times 2x squared, so that's going to be 2b. And in the third term, we can get dx squared, so meaning the x squared can come from the x plus 2 times x minus 2. Or we can get, actually, because this multiplies to x squared minus 4, we'll only get the dx squared, so that'll be just d. Okay, let's see what linear terms we get. We have 4ax, so that's a 4a in here, plus 4bx, so we'll get a 4b here. Then we have, so the cx plus d gets multiplied by x squared minus 4, so we'll have a minus 4cx. Okay. And finally, we're going to have the constant terms, which are minus 2 times 4 is minus 8, so that's minus 8a. And then from this term, we get plus 8b. And from the final term, we get minus 4d. Okay. So this is some work. Another way to do it would just be to FOIL out each term and then look through what happens after you FOIL to get all of the x cubed terms, x squared terms, etc. But you should get the same answer as I did here. So having computed the coefficients of this polynomial, we note that because these two polynomials are equal on either side of the equation, we're going to be able to equate their coefficients. So on the left-hand side of the equation, the coefficient of x cubed is 0. So I can put that here and set that equal to the coefficient of x cubed on the right-hand side, which is a plus b plus c. Similarly, the coefficient of x squared, we have 0 is equal to minus 2a plus 2b plus d. The coefficient of x on the left-hand side is 0. On the right-hand side is 4a plus 4b minus 4c. And finally, we have constant term 1, which is equal to minus 8a plus 8b minus 4d. Okay. So let's pull these equations to the next page. Okay, so we have a system of equations here. And we can use various approaches to solve it. The way that I usually like to do these is by noting common patterns in the equations, seeing if I can cancel things out. So if I take these two, if I take 4 times the first one, I get 4a plus 4b plus 4c equals 0, and 4a plus 4b minus 4c equals 0. And when I subtract those equations, I'm left with 8c equals 0, or c equals 0. Okay. So I can substitute that back in and find that a plus b is in fact equal to 0. Okay, and that's the information we get from these two equations. And now we can use that to substitute into the other two equations. So if this means that b equals minus a, subbing into the first remaining equation, we get 0 equals minus 2a minus 2a plus d, and in the second equation we get 1 equals minus 8a minus 8a minus 4d. This is equal to minus 4a plus d. This is equal to minus 16a minus 4d. Okay, so from this, because minus 4a plus d equals 0, this tells us that d is equal to 4a, which tells me that from this equation, minus 16a minus 4d becomes minus 16a minus another 16a. Which tells me that 1 equals minus 32a, or a equals minus 1 over 32, which tells me that b equals 1 over 32, and c, as we know, is 0, and d is 4 times a, which is minus 1 over 8. Okay, so now we have all of our constants. And the problems that you usually get of this type are not quite so complicated in terms of solving for the coefficients. Okay, a shortcut that may save time but can also be confusing is to plug in values of x that make solving easier. This is known as the heavy-side cover-up method, and it's on Wikipedia if you want to check it out. I generally don't advise people to do it because it tends to get complicated and can be pretty confusing. Okay, so the first thing I'm going to sub in is x equal to 2, because when I put x equals 2 here, a becomes 0, this term becomes 0, as well as the last term. So when I do that, I have 1 on the left-hand side, and I have b times x plus 2 becomes 4, and x squared plus 4 becomes 8. This tells me that b equals 1 over 32. Okay, I can also plug in x equals minus 2, and I get 1 equals a times minus 4 times 8, which tells me that a equals minus 1 over 32. Okay, notice that with these two, with x equals minus 2, both the second and the third term vanish because they each have a factor of x plus 2. Okay, so those are like the only good substitutions, but if we sub in x equals 0, things aren't so bad. So when x equals 0, we get, 1 equals a times minus 2 times 4 plus b times 2 times 4 plus d times 2 times minus 2. And this tells me, because we already know what a and b are, so this is minus 8 times minus 1 over 32, that's positive 1/4, plus 1 over 32 times 8, which is another positive 1/4, plus negative 4d. Okay, so I can so this becomes a half minus 4d, and if I subtract a half on both sides and then divide by negative 4d, I'll get minus 1/8 equals d. Okay. Okay. To find c, we'll do that on the next page, plugging in x equals 1. So plugging in x equals 1, we have 1 equals a times negative 1 times 5 plus b times 3 times 5 plus c plus d, 3 and negative 1. Okay, well, we already know the values of a, b, and d, so this is 5 over 32 plus 15 over 32 plus c, is it positive or negative an eighth? C minus an eighth times negative 3 equals 1. So let's distribute this multiplication here. So we have 20 over 32 plus 3/8 minus 3c equals 1. So 3/8 is equal to 12/32. So we have 1 equals 32 over 32 minus 3c. So as you can see, c equals 0. Okay, and this gives us the same solution as the previous page, but without systems of equations. This is just plugging in convenient values of x. Okay, so we have made we've factored our denominators, we've made our partial fractions, we've solved for the coefficients, and now we have to integrate. Okay, so these are the types of functions you'll get after doing everything above. You can have some polynomials if you did some long division. For polynomials, you just apply the power rule as normal. If you have terms that are a constant divided by x minus a constant, you're going to get logs as your antiderivative. If you have a constant divided by x minus a to some power greater than 1, then you apply the power rule. And if you have cx plus d over a linear term over an irreducible quadratic, then, or power of an irreducible quadratic, then we will see next slide for the strategy. Okay, how do we integrate 1 over an irreducible quadratic? The first step is to complete the square so that the irreducible quadratic is in the form u squared plus a squared. Okay, we don't want any linear terms of u. No u to the power 1. Then we divide the fraction into 2 pieces. So you put the, because recall the numerator is linear, so we'll put the variable part of it in one fraction and the constant part of it in another fraction. So now we'll work on the example, the integral of 1 over x minus 1 times x squared plus 2x plus 5 dx. We just do a quick check. We note that the long division is unnecessary. The denominator is fully factored. Okay, you can check that this second quadratic term is an irreducible quadratic. Okay. So now let's do the partial fraction decomposition of this rational function. Okay, and we're going to do that on the next page. Okay, so we have 1 over x minus 1 times x squared plus 2x plus 5, and we want to set that equal to partial fractions decomposition, which, because we have distinct factors of each of a linear term and an irreducible quadratic, we have a divided by x minus 1 plus bx plus c divided by x squared plus 2x plus 5. Okay, and this is the partial fraction decomposition. Okay, so now we solve in the typical way, clear denominators. Denoms. So we have 1 on the left-hand side. On the right-hand side, we have a times x squared plus 2x plus 5 plus bx plus c times x minus 1. And multiplying out and grouping like terms, we get a plus b times x squared plus 2a minus b plus c times x plus 5a minus c as our constant term. So as before, we set each monomial, we set each term on the left-hand side equal to the corresponding term on the right-hand side. So we get 0 equals a plus b, and 0 equals 2a minus b plus c, and 1 equals 5a minus c. Okay, so from this first equation, we can infer b equals minus a. Okay, and then we can substitute that into this equation to obtain 0 equals 3a plus c, which means that c equals minus 3a. And we can put that into the last equation to obtain 1 equals 8a, which means a equals 1/8. Okay, and in turn b equals minus 1/8, and c equals minus 3/8. Okay, so that means that our rational function 1 over x minus 1 times x squared plus 2x plus 5 is equal to 1/8 divided by x minus 1 plus negative 1/8 x minus 3/8 divided by x squared plus 2x plus 5. Okay, so let's bring that up to the previous page. So we know this integral is equal to the integral of, let's actually make this in some green ink. This is the integral of 1/8 over x minus 1 dx plus, and in orange ink we can do the other one, the integral of negative 1/8 x plus 3/8 divided by x squared plus 2x plus 5 dx. Okay, and this will be our integral number 2. This will be our integral number 1. Okay, so let's go and we'll write a little equal sign here so we're keeping track. Okay, so first things first, we can do integral 1. Okay, and this is not super hard. We have the integral of 1/8 divided by x minus 1 dx. If you want, you could do a u substitution, and it's not, you should be able to just read this off. The integral is 1/8 ln absolute value of x minus 1 plus c. Okay, that's pretty good. Okay, how about 2? So we have the integral of minus 1/8 x minus 3/8 divided by x squared plus 2x plus 5 dx. Okay, so following the advice from the slide earlier, we're going to complete the square in the denominator so we can have a sum of squares. So let's do that over here. Complete the square. So x squared plus 2x, these are the x terms, then we have plus 5 over here. To complete this square, we divide the second coefficient by 2 and then square it. Well, that will give us plus 1. And so since we're adding 1, we subtract 1 over here. So we get x plus 1 squared plus 4. Okay. So this expression, let's factor out the minus 1/8 so it's a little less crazy looking. So this is x plus 3 divided by x plus 1 squared plus 4 dx. And now we're going to want to make a u substitution. So we'll sub in u equals x plus 1. Okay, so let's get this separated off. Okay, so this is our substitution. U equals x plus 1. Du equals dx. So this becomes minus 1/8 integral of, since we have x plus 3 up here, this becomes u plus 2, because u includes x plus 1, divided by u squared plus 4 du. Okay, and as I advised earlier, we're going to split this up into 2 pieces. We'll make this, let's keep this just for this purpose, minus 1/8 times the integral of u du divided by u squared plus 4, and then in this dark green ink we will do the integral of 2 du divided by u squared plus 4. Okay, so we'll call this one number 4. This one will be number 3. Okay. So here we are with number 3. Integral of u du divided by u squared plus 4. Well, we want to use the denominator for a w substitution. So we have dw equals u squared plus 4. dw equals 2u du. I'm going to write this differently so I can just sub out the u du. This gives us, dw over 2 equals u du. And now this becomes integral of dw over 2 divided by w, or times 1 over w. And this is, this is 1/2 the integral of dw over w, which is 1/2 ln absolute value of w plus c. Plugging back in what w is, 1/2 ln u squared plus 4 plus c. And in turn, we plug in what u is, 1/2 ln x plus 1 squared plus 4 plus c. Okay, so that's integral number 3. In terms of integral number 4, we had the integral of, I believe it was 2. Yes, 2 du divided by u squared plus 4. And here we do a trig substitution. So we take u equal to 2 tangent theta. If you're not sure why I chose that trig sub, definitely review the trig sub video. And du equals 2 secant squared theta d theta. Okay, well, when I plug that in here, I get 2 times 2 secant squared theta d theta divided by 4 tangent squared theta plus 4. By the Pythagorean identity, that denominator is 4 secant squared. So I'm left with integral of d theta, which is just theta plus c. Okay, well, we need to convert theta back to x, so we have theta equals arctangent of u over 2. Okay, we have the constant. And then plugging in our value for u, we have this is equal to arctangent of x plus 1 over 2 plus c. Okay, so now we can bring everything together. We knew that our integral was equal to the integrals of 1 plus 2, and we knew that 2 is equal to minus 1/8 of 3 plus 4. So we'll start off with the 1. 1 was 1/8 ln of absolute value x minus 1 plus c. Okay, and I'm going to wait to just put all of the constants together at the end. Okay, plus, or rather, minus 1/8 times 3 plus 4, which is 1/2 ln x plus 1 squared plus 4 plus c, but again the constants we leave out, and arctangent of x plus 1 over 2. Okay, so we have 1/2 ln of x plus 1 squared plus 4 plus, did we have a coefficient here? No, just arctangent of x plus 1 over 2. Okay, so that is the integral. Pretty long problem. If you want to simplify further, you can maybe you can factor the constants a little bit differently. For instance, we could take out a factor of 1/16, and then we'd have 1/16 times 2 ln x minus 1 minus ln x plus 1 squared plus 4 minus 2 arctangent x plus 1 over 2 plus c. But that's not necessary at all. The last line was just as good. Okay, a lot of work, but we eventually got to the correct answer. So to summarize our approach to partial fractions, we start by dividing. Divide via polynomial long division if the numerator has degree greater than or equal to degree of the denominator. Then factor the denominator into linear terms and irreducible quadratics. Decompose into the correct partial fractions format. solve for the unknown coefficients in the partial fraction decomposition, then integrate what remains using completing the square, u sub, and trig sub for the irreducible quadratic case. And that finishes up the long and twisted story of partial fractions. These problems can be pretty exhausting, but I find them to be worth the investment. All right, thank you for your attention.